you are going to be an expert, you will earn money with that. So you have to invest your own money for the future.
It's important to have a model that is robust. You know, we didn't have YouTube. I had a set of Abacus software manuals that were 2 feet high off the table. So there'd be icons everywhere, terminology everywhere. I didn't have a clue what was going on.
Designing a product and doing FEA require a lot of knowledge. So you will have to learn every day. It is the fact that boundary conditions are never perfect.
Dominique and Steffan, 2 experts on my show today. Welcome. Thanks for doing this.
Thank you very much, Jousef, for inviting us.
Thank you, Jousef.
So it's
good to be here.
Thank you so much. It's an FEA session today. So let's get started with a small introduction. Some people already know you. You are legends in the FEA community. Maybe the younger one goes first. Whoever one is the youngest can introduce themselves.
I don't know.
Don't start both now.
You go first, Dominique.
Okay, I go first. So I'm Dominique Madier. I am the director of FEA Academy, a company providing some FEA services, consulting services in finite element analysis around the aerospace industry, but also providing some services around the academic side of finite element analysis because I teach finite element analysis online through courses. So I have more than 25 years of experience in the aerospace industry. And I had the chance to work on many projects in Europe and North America on aerospace projects to develop aircraft, wing, fuselage, empennage, nacelle, engines. So a lot of different analysis, linear analysis, nonlinear, static, dynamic, composite and metallic. A lot of fun at the end of the day doing FEA, focusing on FEA for my customers. And 5 years ago, I decided to teach my knowledge about FEA to the community on the internet. So that is my story.
Interesting. Steffan?
Okay. Yeah, thank you. My situation and background is very similar to Dominique's. So I run Evotech Computer-Aided Engineering in the UK. Again, consulting services into industry. I'm a technical reseller with Hexagon MSc software and also develop a lot of classroom and online training, more focused around software usage than the theoretical aspects, which is more where Dominique comes in. Again, my background, I've got 25 years plus of FEA development, working mainly in the aerospace industry. So lots of structural development for lightweight applications, metallic and composite, and again, a whole host of different analysis types. That's a summary of my background.
Excellent.
And situation.
So it's the perfect example of feeling like an imposter. I'm like only feeling like a beginner when I'm interviewing you. But yeah, anyway. We want to talk about, you've mentioned you're doing a course together because people might ask, why do you interview Steffan and Dominique on the same show? You've done a course together and we'll talk about that in a second. But first of all, I like that you have so much experience, and I've asked Steffan that in our podcast. How do you see the development of FEA tools over the years? Like, what has changed in terms of tooling, and where do you see the future going? Usually that's one of the last questions in the podcast, but I would like to know from your experience, Dominique and then Steffan, how did you see the development of FEA tools, and where do you see it going into the future?
So definitively, we can say that FEA has changed a lot since I started 25 years ago. First, from the software point of view, it has changed a lot. At the pre-post processing level and at the solving level, the change has been amazing because let's start talking about the pre-processing first, because it is always the starting point when we are doing finite element analysis. So the first, what has changed a lot, it is the fact that we are more linked to the CAD than before, and the capabilities of the pre-processing software improved a lot because at the very beginning, I remember 25 years ago, I remember that we were doing a lot of tasks, let's say manually, okay, but now it's taken by the software itself. A lot of process are automatic, and we have a lot of assistance from the software in order to build the EFEM, the simulation, I should say. On the solver side, it's another huge improvement which has been done, for sure now we have the multi-physics. We didn't have that a few years ago. The fact that we can model a lot of interaction between the components, model the fastener, model the contact, define the contact is more easy. It's easier, and also the performance of the solver themselves linked to the performance of the computers. It improved a lot. I remember, let's say, 15 years ago, a 500,000 degrees of freedom EFEM, it was a huge EFEM, Now it's a small EFEM. We cannot imagine an EFEM with less than 1 million degrees of freedom now. It doesn't exist. And it's a standard, okay? So this makes the work of the EFE analyst more interesting, because we can capture more effect when we are doing our simulation. So yeah, they are the major improvement. For the future, I think it will be. I think more is coming. Okay, because now what we can see that first, finite element analysis is everywhere. Okay, we cannot imagine a product design without finite element analysis. So finite element analysis now, and it will be more in the future. It's embedded in the process of development of the products. Okay, so for the future, what I see, it is this very promising meshless approach, because now we are still dependent on the meshing process, which is time consuming, less and less thanks to the powerful of the new pre-processing software, but it is still time consuming. So I think that this new technology, the meshless technology, is very promising. Personally, I only tested it a little bit, but not that much. So I cannot talk a lot on it, but I think it is the future. This meshless. Also, the future, it is this what we call digital twin. And okay, EFE itself, it is not the digital twin, but EFE will be more part of the digital twin. So I think it is another development that will come related to simulation in the future. So I don't want to speak too much, and I will let Steff talking about that also.
Yeah. Definitely. Perfect segue, by the way, into Apex, because Dominique talked a little bit about user interface, which definitely has improved a lot when we talk about Apex. So maybe, Steffan, what's your view on the past and the future, maybe also the status quo?
Yeah, I'd echo everything that Dominique has covered, really. So I'm thinking back to the first time when I picked up FEA using a commercial tool and Abacus we were looking at, and the pre and post processing and the solving was painful. It was absolutely painful. You would spend a long time simplifying models to get you to a mesh that you could handle, and then you would try and solve, and you would fall over, in terms of singularity issues and computing resource problems and all sorts of things like that. So obviously more recently, computing has got more powerful. It's become more available to people. Software has improved. It's improved in terms of capability, but also in terms of distribution. So many years ago, you'd need some pretty hefty computing equipment to maybe Unix-based workstations to run FEA software. People can run stuff on laptops now using trial licenses, for free access to capability. So there's huge advances in terms of access and learning experience that people can take advantage of, and that's just a general access to engineers. We have to remember that FEA is a tool. So if you want to engineer a structure, the better the tool, the better the job you can do with it. So we're really in a position now where we can really start to optimize structures rather than simply verify that a legacy concept is going to work. So you can look at many, many different iterations of a design much more quickly than we could ever do previously. Dominique's mentioned was multi-physics, so you can look at things like, structural nonlinearities now in a time frame which we just couldn't do, in the past. So, the way I see this stuff going is that software is getting easier to use, more easily available to people, more powerful. So we can just do more things, better things to develop the structure that people are going to be looking at.
Maybe on that point, Steffan, and maybe also Dominic, you can add your 2 cents here. Is the question would probably be, future tools might facilitate a lot of tasks. So the question would be, in the future, do you see that an engineer would either be a CAD engineer or an FEA engineer? Or do you think like both will be combined in the future, so that an engineer would have one tool, but which would facilitate CAD and FEA at the same time? So an engineer wouldn't need to be an expert in FEA or an expert in CAD, but he could know both a little bit and would use one tool which facilitates already the kind of the gap.
Yeah, I think probably what I'd say on that is that separation in terms of engineering role really does depend on the size and the type of company that people are working in. So in smaller companies, people need to have more general skills to be able to do a full engineering role. In a bigger company, people tend to get separated. So Dominique's mentioned his background in the aerospace industry, and the same for myself. So in that kind of scenario, you tend to have design engineers who are running CAD tools, and then structures engineers who are doing the analysis and simulation. I still think that there's going to be a level of expertise that's required to do, a full engineering workflow in specific areas. But certainly those barriers between discrete disciplines are definitely coming down in terms of the companies that I'm working with.
Interesting. Dominic, what's your 2 cents?
Yeah, I can only agree with Steff about this point. And we know that merging CAD and FEA, it is the dream of the companies who manufacture those software, and they are trying that very hard. But according to me, it's not a success so far. I didn't see any solution merging the CAD and the FEA efficiently. I would say we have some FEA solutions which have some CAD capabilities, but it's not that good enough in order to do a complete design work on those tools. So I think it's too specific. As Steff said before, designing the design workflows and the FEA workflows, I think, are too specific in order to be able to merge them together. For sure, we know that we have tools where we have the CAD and FEA embedded in themselves, but what I have seen is that nobody are using them because there are too many limitations. If you have the tools doing CAD and FEA, at the end of the day, one of the two capabilities will work well, will do what we need, but the other capability won't do the job. Okay, so we cannot say that it will not happen in the future. Maybe we will have the dreaming platform where we can do everything, but so far it doesn't exist. We try, some people are trying, but it doesn't work very well. And to conclude on that, I totally agree with Steff. Designing a product and doing FEA require a lot of knowledge and very different knowledge. And it's very difficult to have all the knowledge to do a good design and to have all the knowledge to do finite element analysis. I think we absolutely need to segregate those two disciplines in order to make sure that we are doing that properly. It is my opinion on that.
That makes a lot of sense, yeah. Talking about being an FEA expert, what skills do you see, especially maybe people taking your classes, do you think is missing? I feel in university, they do a very good job most of the time teaching the theoretical or the fundamentals of FEA, like how do you derive it, strong, weak form, and all these kind of things that you know about. But when it comes to practical applications, theory doesn't get you that far. So in terms of practical skills, what do you say? Let's phrase it in like top 3 skills an FEA engineer needs to have in order to be successful in the industry? Maybe Dominique, if you want to continue.
Yeah, that's a great question, Jousef, because it is something that is problematic today for people who are claiming that they know FEA. Okay, as you said, most of the time people they learn the basic theory at university or college, but sometimes they don't know what they don't know. Okay, they don't know what they know, and the reason why is because they learn basic theory, and after that they learn the software, the FEA software. Okay, at the end of the day, we have to learn FEA software because we cannot conduct the simulation without the software, obviously. But in order to be able to do this bridge between the theory and using the software, you need to learn modeling techniques. Okay, because knowing modeling techniques permit you to do the right assumption in order to capture the effects you want to capture with your simulation. Because we know that we can capture a lot of effects with our simulation, and behind each effect we want to simulate, there are many assumptions we have to do in order to make sure that we submit the right set of equations to the solver. Okay, and learning modeling techniques, it is the key point in order to make sure that we are doing the right assumption and to make sure we are submitting the right set of equations to the solver. And it is important to make sure that we submit the right set of equations to the solver, because the solver will always provide you a response, an answer, even if the set of equations you submitted is wrong. Okay, so it is why when I teach FEA, I want to tell people that don't miss the step 2, which consists in learning modeling techniques. And it is the problem I can see we have with students which come from the universities. This step, learning modeling techniques, there is a problem with this step. They jump from theory to the software. And for sure, learning the software is very fun. It's more fun than learning modeling techniques. But if you don't know the modeling techniques, you won't be a good FEA analyst. Okay, you will miss something.
Good point. Steffan?
Yeah, same really. You know, it's very difficult to go from a theoretical, potentially mathematical background in a subject, and then to be faced with a graphical user interface to allow you to understand how a structure is going to behave or develop a structure in a way that's going to make sense. So having a good grasp of the theory, the modeling and simulation techniques, and then being able to apply those into a software environment is really important. I mean, one major aspect of any sort of reasonable FEA workflow is the ability to look at the model that's been built, look at the results that have been generated, and then some way be able to say, I'm going to verify those results against something I know from reality. So generally speaking, that would be maybe taking something very simple and comparing that or verifying that against a very simple analytical equation or hand calc or something like that, and then to be able to say, okay, I'm designing an aircraft wing, or I'm involved in the design of an aircraft wing, but ultimately, do I know how to set up a cantilever beam and show I can apply the loads properly and understand that I've got the correct displacements and the correct stress distribution, before I then start to look at something more complex. The ability to bring things back from what you're seeing in a piece of software to something that makes sense, through a simple calc, a simple spreadsheet, set of numbers. I'm doing this stuff all the time, for some pretty complex. I'm doing a lot of nonlinear work at the moment, but the ability to bring it back to fundamentals, to bridge the gap from theory to ultimately a report that somebody's going to see is imperative, and I mean, probably jumping the gun a little bit here, but some of the work that I've done, well, myself and Dominique have been involved with in terms of the online course that we've been releasing does cover a lot of these building blocks in terms of where people need to be focusing their efforts in terms of making them or at least on the road to becoming a successful FEA engineer and having the tools in their pocket to be able to do that.
Very good. We'll talk about the course in a second, as I promised in the beginning.
Yeah.
A very good point that you mentioned verification, which also comes with the term validation. Now it's very, very important to distinguish those two. What is verification? What is validation? Steffan, could you maybe explain what is verification? And then Dominique does the validation part. So
okay. So, well, I've written and authored and overseen many FEA verification reports over the years, and have been called up by various suppliers or clients and suppliers in terms of the terminology that's used. So the standard terminology, as I understand it, is that verification is the means that you will go through to demonstrate that your model works correctly mathematically based on what you're trying to achieve. So you can verify the overall response. Validation, I don't know whether I'm probably jumping the gun in terms of what Dominique might say. Generally speaking, validation would then be comparison between your model response and some kind of physical response, maybe a physical test. So verification, ensuring correct numerical behavior, validation, comparison against a physical test. Mm-hmm. I don't know if that's your understanding of those terms, Dominique.
Absolutely, it's very well explained. It is exactly that, and generally we start with the verification, because at the beginning, when we want to run the FEM, we don't have the test results, so we start with the verification. We run the FEM, and as soon as we have, we are doing some analysis after this verification using the FEA, we are able to tell to the test group where to put the strain gauges in order to record the data. They provide them that, and we do this validation. We call that, in the aerospace industry, we call that also correlation, where we do this comparison, calculate the validation factor, and maybe probably if we have discrepancies between the FEA result and the test, we are doing some adjustment, calibration to the FEA, and that's it. So it's a huge process, but I can speak only for aerospace, but in the aerospace industry, it's a very long process. So because usually we are installing a lot of strain gauges on the aircraft, because we are doing full scale tests in the aerospace industry on a full aircraft. So it's a lot of data, a lot of load cases and a lot of recordings. So it takes a lot of time to do this kind of work. But it's fun, because at the end of the day, you verify that your simulation, your predictions match the reality. And most of the time it matches, because we are following the correct modeling, the correct modeling process. So most of the time it match, and it's very satisfying to see this match.
Yeah, definitely. When we talk about verification and validation, I think Steffan mentioned earlier on doing analytical or like hand calculations. Now the question might come up, which is, I don't have an analytical formula describing my problem. Could be a crash test. There's no analytical formula to describe a crash test. How do I know my FEA results are accurate enough? What can I do? Maybe Steffan can go first.
Okay, so there are many analytical methods to describe simple mechanical situations. There are also, I'm just thinking of NAFEMS, the body that looks after a lot of FEA, CA distribution and usage in industry. They publish a lot of benchmark examples. Mm-hmm. There may not be the exact scenario that covers what you're trying to develop, but you should be able to take a step back and if you're looking at maybe some impact, dynamic analysis, then you've obviously got material behavior in there, you've got mesh sensitivities in there, you've got loading sensitivities, etc. So you should be able to take those complex parts and separate them into their constituent parts and ensure that you understand and are able to justify the behavior of each one of those bits before you start mixing them up and looking at the situation as a whole. One very, very useful approach is, looking at very simple models that run quickly If something's going to fail, you want it to fail fast. So you can understand, again, I mentioned I'm doing some nonlinear work at the moment. So don't build a 1,000,000 degree of freedom model to have to wait, 2 hours to see that it's going to fail.
Yeah.
Build a very simple model, understand sensitivities, understand the behavior before you then start to increment up in terms of the complexity of the situation that you're looking at.
Makes a lot of sense. Dominique, is there like any metric how we could define that we're approaching convergence, for example, or is there any other metric we could see that a use case we've never seen before is converging or is usable in terms of FEA?
What kind of convergence are you talking about?
For example, if we talk about mesh convergence, like we know the classical mesh convergence, but we don't have analytical formulas at our fingertips, or maybe even benchmarks, as Steffan has mentioned them. What can we do? Any other solution?
Yeah, typically what we're doing in the aerospace industry, there is no formula. I don't know any formula for the mesh convergence. I don't know on your side, Steff, if you know some formulas, but we don't have that. When we need to let's say do this convergent validation, we are definitely doing the mesh convergence by creating some refining the mesh and comparing the results. Let's say I give an example like that, a large cutout like a cabin window in a fuselage or a PAX door cutout in a fuselage. So for sure we have stress concentrations at the corners of such a structure. So we need, in order to capture the correct stress, we need to conduct the convergence study. So definitely what we are doing in those regions, we refine the mesh step by step and validating the convergence by extracting the stresses or the strains. And we plot the convergence curve and to validate the convergence. It is as simple as that, but there is no rocket science formula, something like that. It's very basic. We mesh, we compare, and when we are able to plot a convergence, that's it. We claim it's converged. Very simple at the end of the day.
That was bad on my part, Dominique. What I actually meant, I think we mean the same thing, but I formulated it a bit difficult, which is assuming I do a test, for example, a crash test, could I assume that once the mesh has converged, that my simulation will be accurate? Let's just reformulate.
Yeah, but I see in the other way, you have to converge the mesh in order to claim that your solution is correct.
Got it. Then we would run into other problems, which is, are the boundary conditions correct? Now the question is, and greetings to my colleague Lukas Skotnier at that point, who says, I think, don't correct me if I'm wrong, that boundary conditions is probably one of the most difficult things to do in FEA. What would you say to that?
Oh, yes, that's a very good question, because it's always the key problem when we build an FEA. On my side, I don't know you, Steff, but I find that it's not easy to define the boundary conditions, and you know why? Mm-hmm. It's because we use FEA to solve complex problems. We don't use FEA to solve simple problems, because if we have a simple problem, by the way, we are doing to use a closed form solution, an equation. We have references for that, Brune, New in the aerospace industry, NACA, ESDU, but for simple problems, we don't use FEA. But when we use FEA, it is because the closed form solution are too restrictive or too conservative. So we do an FEA. And then it means we face a complex problem. And when we have a complex problem, with a complex problem, I should say, comes complex boundary conditions. So it is the reason why it's not always very easy to define the boundary conditions. So, but the best tool we have, in order to define the boundary conditions, the best tool we have is our engineering judgment. Because what is the objective of the boundary condition? What are the objectives? The objective is to represent the reality, how the piece we want to simulate is grounded, is interfaced with the environment in the reality. So our engineering judgment will tell us how our part is interfaced with the outside, with the environment. So it is what we have to do. We have to replicate those boundary I don't want to use the boundary condition term for the reality, but yes, let's say the boundary conditions of the reality and replicate them into the simulation with constraints, enforced displacement, forces. We have a lot of contacts also. We have a lot of different objects we can use in order to generate the boundary conditions. So this is the key point. The key point is using our engineering judgment, okay? Because when we think about the objects we have in order to define the boundary conditions, it seems that those objects are mathematical objects, okay? But we can relate them to the reality. And it is really what we have to do with our engineering judgment. But as you said, it's not an easy task. It's always the most challenging task when we develop an FEM.
That makes a lot of sense, Dominique. Thank you so much. And Steffan, would you add anything to that? And also, how do you get your hands dirty actually learning how to apply boundary conditions in FEM?
Yeah, well, I think as with many things, certainly in FEA development, it's important to have a model that is robust in terms of its behavior and the output that you see. So let's imagine a scenario where you're not 100% sure about a particular boundary condition. Maybe you've got some, I don't know, bracketry attached to a piece of structure and you're interested in the bracketry. Then you can understand. You can start to understand the sensitivity to the model response. Do you assume that the backup structure is infinitely rigid, and therefore you can use maybe a clamped boundary condition? Is there flexibility in the backup structure? So maybe do you have to maybe introduce some kind of local stiffness at the interface? So these kinds of things will give you, again, using the sort of engineering judgment that we have, these kinds of things would give you an idea of how sensitive the situation or the particular simulation is to how you are loading or constraining a given system. And if you, I suppose, worst case scenario, if you show that the model response is completely different, based on infinite stiffness or infinite flexibility, then maybe you're going to have to introduce the backup structure into your model so that you get the true load path through the structure. So it's not simple. I mean, again, there's no handbook you can pick up and say, for situation A, use this, B, use this, blah, blah, blah. But, having judgment and a mind that you can understand and investigate the problem will give you, or get you a long way down the road to allowing you to perform an analysis that's correct.
Yeah,
that falls.
If I can add something, Jousef.
Sure, go for it.
There is something very important about boundary conditions. It is the fact that boundary conditions are never perfect. Okay, except if your problem is simple. But as I said, we are using FEA in order to solve complex problems. Okay, so with complex problem, forget to find the perfect, the ideal boundary conditions. It doesn't exist. Okay, it's very important to have that in mind. But as Steff said, by doing the sensitivity study, we can converge with something which is representative and acceptable in order to have accurate results.
Mm-hmm. I feel like even replicating a real world model would be a success in itself. So brings me back to the quote always from George Box, the British statistician: all models are wrong, but some are useful, which I think summarizes it pretty well. I think boundary conditions falls under the aspect of modeling techniques, which brings me to your course that you've launched together. Modeling techniques, what do you cover in your courses, and how do you approach or make people become better? I wouldn't say expert, maybe you would say expert, become better at FEA, how they tackle FEA tasks. Maybe Steffan, you can go first if you want.
Well, I think probably Dominique would give the full description of the aspects that he's involved with. But in my words, really, we're looking at fundamentals and theory, modeling applications, and then seeing those techniques in a real commercial software environment. So personally speaking, I've developed quite a few examples to support the learning that Dominic goes through, all done in a contemporary tool. The tool is MSc Apex, a tool I'm very familiar with and very active in terms of distribution into industry. But the tool is I wouldn't say totally irrelevant, because you want to be able to do stuff quickly to aid the learning experience. But the essence of the course is to give people the theoretical knowledge, the practical example, and then the ability to run through those examples or to see those examples in a contemporary software environment.
Mm-hmm. Dominique?
Yeah. Okay. To speak about this FEA learning process is very interesting, because as I said at the beginning, the 3 stages of FEA learning, of the FEA learning process, is learning basic theory, learning modeling techniques, and after that learning a software. And it is the goal of the course we are proposing now, the on-demand course. It covers exactly the 3 steps, because I cover basic theory and modeling techniques in my lectures, and then Steff is covering the FEA workflow, as he said, showing a very advanced example and FEA workflow in Apex. So the objective is really that, to bring the students and the engineers through the 3 stages, to make sure that they don't miss a stage, because it is what we observe now. People are jumping or skipping some stage. And it's not good at the end of the day for the FEA learning process, because at the end of the day, we generate engineers who do not understand very well what they are doing with their simulation. And it's not good, because at the end of the day, the product development is not optimal. You see what I mean? So FEA it's not simple. So I mean, in terms of practicing FEA, it's not simple. Okay, so learning FEA is not simple. Okay, there are many stages, and we have to follow the stages and do that step by step. And as Steff said, and I love when he says that, he said that using simple example, because it's complex at the end of the day, because we are simulating very complex effect, very complex structure, very complex assemblies, but it is based on simple effects that we have to put together, and simple modeling techniques that we have to put together. So it is the reason why the examples are simple, not very complex, but it permits the students and the engineers to understand each concept one by one in order to use them all together in a more complex analysis. Okay, so this is really the objective of the course.
Mm-hmm. Very cool. And I will definitely put a link down in the description. If anyone wants to check out the course, feel free to do so. And if people want to experience the teaching style of Steff and Dominique, which is, by the way, excellent, they can also come to the 5-week course that I'm offering. And Dominique and Steff will give an introduction to FEA and do some hands-on tutorial as well. Really cool. Question now would be, the phone rings, 18-year-old Steffan or Dominique picks up and says, by the way, I have an FEA problem. I'm struggling. Can you give me some tips on how I approach my FEA problem? What would you tell your younger self? Maybe Steffan, if you want to go first.
Yeah, okay. Well, my younger self, I think we mentioned this the other day, Jousef, when we spoke together. My learning experience, maybe over 25 years ago, I had a set of Abacus software manuals that were 2 feet high off the table. And it was pretty advanced stuff. There wasn't a lot of simple examples to follow. The software was pretty opaque. So there'd be icons everywhere, terminology everywhere. I didn't have a clue what was going on, So I was relying on, in the university environment, people that knew just a little bit more than I did, to help me in terms of the learning. We didn't have YouTube. A video demonstration was light years away. So yeah, the beauty today is that people have got, like I say, they've got access to so much learning experience, learning content. They've got access to forums. They've got access to video demos, courses and what have you. They've got access to free software, that people can use. So you can do this stuff on a relatively inexpensive laptop at home. You don't need to be in a work environment, with really fast machines. One of the really attractive parts, I think, of what myself and Dominique have done with this course is that Apex as a tool has been developed to be so easy to use that you're learning FEA. You're not learning how to find the icon, how to find the form. What does this word mean? What does this number mean? It takes that away because the software is straightforward. There are on-demand videos on how to use the software built into the environment. So I think what we're doing here, the combined offering is not really been seen before. Laying out the theory, laying out the modeling analysis fundamentals in such a clear and easily accessible manner, and then showing the application of that in a software environment that's just so easy to use that it takes the headache away. You can address the problem that you want to look at, or at least follow the learning to be able to take that onto your own examples. So I don't know if that was a particularly good difference between the 18-year-old me and where we are now. But if my son, for example, was going to be picking up FEA, he's 12 years old, so it's maybe not quite the right time for him. But the opportunities there for learning are light years away from where I was, 25, 30 years ago,
Yeah, I see. That would also be interesting, like when we see your son having to do Apex, like he's 12 years old, you tell your son, you have to do Apex now. You're building a model and you're simulating it right now. But what I would love from your side, Steffan, is what you said is actually on the scarcity of resources that you had back then, also Dominique, because I feel a lot of people nowadays, they fall into this analysis paralysis mode, where they're like, I have 1 million of tutorials now. Okay, let me watch that tutorial. And then they watch 50 tutorials and haven't even started to tackle their own problem. So I feel to some extent having scarce resources also teaches you a valuable lesson, in my opinion. That's just my philosophical answer to what you said. But yeah, Dominique, what would you say? How would you talk to your 18-year-old self?
Yeah, the fact that, as Steff said, the fact that now the students and engineers have access to a lot of different resources, it's a huge advantage. Okay, and as Steff said, even free resources. Not only free resources, because some courses you have to pay for that, but it's available. Okay, even at home, and you connect the internet, you stay at home and you can learn. Okay, so definitively it's a huge advantage. But also another advantage I see now for the learning process, it is the fact that people have access to coach. Okay, you, Steff, myself, Łukasz, guys like that, Tony, they are available on the web. They offer their services on the web to teach online. Okay, and I think the students should do that more than they are doing now. They should ask us more help. On my side, I see a lot of people asking help, but I would like to see more. You see what I mean? Because we have an amazing experience in we are talking about FEA, in FEA simulation. So, and we are open to share our experience. So students and engineers should know that, and they should use they should use us as coach in order to learn FEA.
This is such a good point, Dominique, because what I was thinking is time is the most valuable resource that we have. It's limited. And the thing is, what people don't realize, if you offer a course, you, Steffan and Dominique, is you pay a specific amount of money for that course, depending also where you come from. Obviously, not everyone has the same possibilities in terms of money and so on. But it's like buying your experience, both of your experiences, for a few $100 is, I think, for me at least, a no-brainer. Because when I think about buying a course, sometimes it's like costs like $1,000, $1,500. Sometimes for me, that's a no-brainer because I'm buying into the experience that the guy has who's teaching me. So sometimes really it's a no-brainer. It also depends who is teaching and how the teaching style is, and if it actually applies to my personal life, my professional life. But I think from my perspective, buying a course for $500, $600 I think from my perspective would be a no-brainer because it buys you time, which you don't have the older you get. Like it's getting less. What do you think to that?
But yeah, if when you want to learn something, something advanced, let's say, the first thing you want a good teacher. Okay, because many teachers are teaching many things on internet, but not all teachers are good at teaching. Okay, so I think I agree with you. Paying for a course with someone who has a lot of experience, it's good because you are going to learn straightforward the right thing and the right way. Okay, so to me, I think it's good to pay for a course. As Steff said, there are many free courses on the internet. But I'm not sure that following only those free courses, you will obtain what you want. Okay, especially in FEA, which is a very complex discipline. Okay, so at the end of the day, for sure, you will have to pay a coach or on-demand course, a live course, in order to reach a certain level. Okay, but it is what it is. You want to become an expert. And when you are going to be an expert, you will earn money with that. So you have to invest your own money for the future. That's it.
At least you said it now, because if I would say, people would be like, yeah, he only wants to sell his course. But I think it's exactly that point. You buy to get some time back, but also you buy for expertise that people are giving you. It's the same as reading a book. People have put all of their knowledge in one book. By the way, I have your book next to me. And you're buying that book to get that knowledge, which is condensed and picked from several places and your experience into one resource. I think a lot of people forget that. Steffan, what's your opinion on that?
Yeah. Sorry, Dominique. Yeah, absolutely. Yeah, obviously I mentioned the free resources that are around, but I think having the ability to do a focused, guided route through learning, which is exactly what we're proposing with this course, from effectively no knowledge to be able to run some pretty complex stuff, and it all being laid out in a very clear, concise manner, and being able to go back and redo sections and lessons if necessary is really important. The other aspect as well, which maybe Dominique might want to talk a little bit about this, but in terms of the online learning system or management system, there is a forum area where people can ask questions, and it's not just myself and Dominic who can reply. I believe there's the capability for other people to engage in terms of a student's learning experience. So it's not a case of just being left on your own. You take the course, you're fully immersed in the learning, and you're also able to engage with the community, myself and Dominic included. But any questions then would become effectively an FAQ in terms of people's learning experience, and other people can benefit from that as well. So there's a lot. There's a lot there in terms of access to the content, but also access to expert knowledge to support people's learning.
Mm-hmm. Again, maybe some people wouldn't call it a no-brainer to get the course, but I would call it like that. And maybe it also buys you time and also buying into the expertise that you guys accumulated over the years. So if people want to check it out, they can. Link down in the description. Also, if you want to ask Dominic or Steffan some questions, I'll also put the LinkedIn link to their profiles down in the description. Okay, we're almost approaching an hour. Any closing remarks from your end? Any last words to the FEA community out there? Maybe Dominic, you go first, and then Steffan. I think we can wrap it up.
You mean the last word for the FEA community is, if you are interested with FEA, you will have to learn all the time. Okay, it is the key of FEA. It evolved a lot. As we said, it's very complex. You can capture many effects with FEA. So you will have to learn every day. Okay, and it is why FEA is so fun. Okay, but take it easy, take it that step by step. And Steff and myself, we are here, and even you, Jousef, we are here to help you for that. So as I said, do not hesitate to contact us and to ask for our help, because definitively we are here for you to learn better FEA.
Excellent. Steffan?
Yeah. I would echo that sentiment exactly. You know, I think one of the I talked about this with somebody else on another podcast. One of the great tools that you can arm yourself with in terms of developing your FEA skills is learning how to learn. So with having a really good foundation in terms of learning this type of technology and application, it will give you a good platform to be able to address the next problem that you might come across, you know, the more advanced areas. You know, so foundation knowledge is absolutely imperative to develop in this area.
Awesome. That sums it up. Also, learning how to learn. I'll put a link down in the description as well for a Coursera class from, I think, Barbara Oakley, who explains learning how to learn, how you actually approach a new topic. Really, really interesting.
That's good.
Excellent.
Cool. With that, thank you so much. It was really an honor hosting you two. And we'll see hopefully each other in a future episode of the podcast. Who knows?
Thank you very much.
Jousef.
Thank you so much.